We've been talking about earthquakes, and we just did our earthquake demo outside. And these different motions of the earthquakes, with the lateral motion, the compression motion. Okay, how does that affect the layers of the earth? That's what we're going to be talking about for the next 6 slides. Chemically, the earth can be made of the crust, the mantle, and the core. It's because they're chemically different. The crust is not exactly the same stuff as the mantle, and the core is really not the same stuff as the mantle or the crust. So chemically, they're different. But physically, they break down even more than that. So the crust can be broken down into the lithosphere. You have the asthenosphere, which is part of the lithosphere and the mantle. You have the lower part of the mantle, you have the outer core and the inner core. So these are the different layers of the earth. Okay, so thus the layers of the earth poster. I've got another one of these outside on the wall that you guys just had your backs up against. That's even more detailed and better. Layers of the earth. Aha! Layers of the earth. So this side, layers by composition. Now I'm going to try not to insult your intelligence, and I'm sure somewhere around kindergarten, they told you that there's the crust, the mantle, and the core. Right? Does everyone, you all know that there's the crust, the mantle, and the core?
Yeah.
Now I do.
Okay, now you do. Alright. Well, I want you to think of the crust, the mantle, and the core like a raw egg. In a raw egg, you have the egg shell, the egg white, and the egg yolk. And that's actually a very good analogy because the egg yolk tends to be a lot more solid. Actually, that's a terrible analogy. We're just going to go with the picture of the egg yolk, the egg white, and the shell. That's the earth. That's the earth. But it really breaks down more than that because we have the crust, and the crust isn't even the same everywhere. We have ocean crust, we have continental crust. We have the lithosphere, which is part of the ocean and the continent, and a little bit of the mantle, and then we have the asthenosphere, which has the upper mantle and part of the lithosphere, the lower mantle, the outer core, and the inner core. Okay, Ben?
Yes.
Okay, so these are the layers of the earth. Well, this is a section taken, I don't know if you guys noticed this, so like if you blow up this little square right here, it blows up to here. This is a diagram from your book. So here's that upper mantle. This is the asthenosphere. Now, if you can't pronounce that, fine. I really don't care if you can pronounce the asthenosphere. You should be able to pronounce the lithosphere. Well, this is an important chart. Why is this an important chart? This tells us a lot of things. For example, down here, no earthquakes. Why don't we have earthquakes down here? Because it's what? Well, it's not necessarily lava. It's the mantle. There might be spots where there's magma, but it's not all magma. It's a mostly solid rock. But why don't we have, I mean, you got the right concept. Why is it that there's no earthquakes down here when there's lots of earthquakes up here?
Because there's nothing to move.
Was that?
Is there no room for the things to move quickly?
Oh, you guys are starting to think on the right track. Think about the composition of what's, well, not composition, the state of matter.
Wait, is it on the top? It's gonna straight up
Whoa,
solids.
what was that? What was that?
I said it's like pushing it down, so it's like it doesn't have much room to move.
No, you guys are close.
I think I got it.
You think you got it?
It's kind of on the top. It's two solid surfaces pushed on each other like that.
Okay.
And down there, it's like two kind of liquidy.
Oh my gosh! First person in all my classes to get it. Okay. Up here is like the eggshell. No matter what you do with the eggshell, it's going to crack. Right? Because it's hard. And things just tend to crack and break. So a better example, if you guys either see those little candles, little skinny white candles?
Yeah.
Well, if it's a cold candle and you try to push it in the middle, what's going to happen?
Snap.
It's going to snap because it's cold, it's brittle. Well, if you light the candle and the very top of the candle you try to break, it's going to be kind of mushy. It's not really a liquid yet because it's still kind of hot wax, but it hasn't melted all the way, but it's not really brittle yet. And if you try to smear that everywhere, what happens? It smears. So if you have down here the earth moving, that's like hot wax. So you have that, oh, it kind of moves. There's nothing stopping the movement. It's kind of ductile. Up here, it's really brittle. This would be like the candle's nice and cold, so we try to move it and it cracks. Okay? So this is why we have no earthquakes down here and earthquakes up here. Okay? So that's one thing that we can learn. What do you notice about the different crust material? Oh, different colors, yeah. Oh, it's thicker and thinner. This is very thin. This is actually quite thick. What do you notice about the thick stuff? It's doing something kind of cool. Well, rigid would be like, this would be a mountain, so this is the continents, right? So the Rocky Mountains could be this. Is that an answer one, or just an epic stretch?
Epic stretch.
Okay. Think of a waterbed. Okay. If you sit on a waterbed, let's say I had a 17-pound dog. If my 17-pound dog jumps up on the waterbed, is he going to make a big hole in the waterbed?
No.
Or is he going to like depress the waterbed that much?
No.
What about my 65-pound dog?
Yes.
Yes. Now what about my 200-pound self?
Yes.
Yes. The bigger you are, the more you kind of sag into what you're floating on. Because the crust is quite literally floating on the asthenosphere. Okay, or on, well, a better way to say it would be on the mantle. The crust is literally floating on the mantle. Important point. All right, I have some notes for you to take. So write these down as I talk about them. Okay. The crust is that outer solid layer. And it goes anywhere from 5 to 70 kilometers. Well, if 100 kilometers is 60 miles, we already ascertained that, then 70 kilometers is, let's say, roughly 40, 45 miles, something in there. I mean, obviously that's a very rough estimate. 40, 45 miles. Well, I live, depending on which route you take, almost 30 miles away. So it takes me 1 hour to drive home, typically. So that drive, that length, if you could turn that up on its end, that is probably an average thickness for the crust, because 70 is going to be more of an extreme thickness for the continent crust. Okay? I like to run. I'm not very good at it, but I do enjoy it. I get on my treadmill, and lately I've been trying to push the boundaries of the 5K on the treadmill. So my goal now is to see if I can run for 40 minutes every time I run. Well, that's pushing about, right now I'm running about 4 miles. And I'm really happy to do it. Keep my old body dying on a treadmill. Well, 4 miles is actually a mile longer than a 5K. Because a 5K is only 3.1 miles. So, if you figure just the measly amount of space that 3 miles is, that's how thick the ocean crust is. It's actually very thin. Very, very thin. Shallow and thin. Okay? But what do we notice about this? What is grams per cubic centimeter? That's mass per unit volume. What is that a measure of? Density. What do we notice about the continental crust density compared to the oceanic crust? It's not that it's thicker. Thicker would be how deep it is. No, it's more dense, right? It's more compact. Well, the oceanic crust is made of mafic rock. Mafic rock has a lot of what mineral in it to make it dark and heavy? It rusts. Iron. Okay? Iron. Good. Well, if we look back here, this really iron-rich rock is actually more dense than the continental crust. Who knew? Right? If I take a bottle, let's see if I can make this bigger. Okay, this is my bottle of salad dressing. Okay, I tried to draw it differently, but I ended up just drawing something inappropriate. So, this is my bottle of salad dressing. Now, in my bottle of salad dressing, I like to have like oil and vinegar, like vinaigrettes. One of my favorite things is a raspberry vinaigrette. So you have the little pieces of like the peppers and stuff that collect at the bottom. Then you have this fluid here, and then you have a fluid here. And if you just leave it on the shelf or in the fridge, it just tends to separate, right? It's called differentiating. What is the stuff on the bottom made of? It's what? It's the vinegar solution. Vinegar is water-based. So for the sake of understanding it, we're going to call it water. What do we have on the top?
Oil.
Oil. Depending on how much oil you have is how healthy your salad dressing is. Okay? So here's your oil, here's your water, and here's some other heavier stuff on the bottom. Okay? Which one of these is more dense?
Oil? No, the one bottom.
This is more dense.
Because it's the bottom. And denser stuff works.
Okay, the less dense stuff will literally float on top. So the oil is floating on the water. This is 2.7 grams per centimeter cube, or cubic centimeter. Okay, here we have 3.0. Down here we have about 3.4. Do you kind of see what's going on? That this stuff is truly lighter and it floats here. Well, what if the oceanic crust, which is typically next to continental crust, what if it crashes together? Which one's going to go on top? Which one's going to go underneath? Yeah, this one is going to go down and this one will stay on top because it's literally lighter and it's more buoyant. Okay? That's an important point. What? I know, but I like to share. Actually use it occasionally. Okay. Okay. So here we have the crust and the lithosphere. Now let's talk about the mantle. Remember how I said 3.4 in the mantle? Okay. It's made of very silica-based rocks, a lot of like ultramafic rocks, like olivine minerals and very, very iron-rich rocks. Like, let's see, you have like komatiites and peridiotites and some other neat stuff down there. Okay. This one's really thick. This is kind of the thickest layer. This is the whole mantle. So if we look at the asthenosphere and the mantle put together, their rocks are so hot, but they're not quite liquids. They're very easily deformed and easily moved. They are even capable of flowing in one direction, or two directions. Okay, so we see convection, at least we theorize that there's convection in the mantle. Okay, so here's the mantle, or part of the asthenosphere. Did you guys get this? Questions on the mantle or the asthenosphere? Okay. Okay, I gotta move on here.
Okay, you can go ahead.
2. Okay, let's just skip the core. Okay, now let's talk about the core. What do we notice about the core?
More dense.
How much more dense?
And a lot.
Like 10 times more dense, right? Now we're up to 13 grams per cubic centimeter. Why? What is the core made of? Is it made of rock?
No.
No, it's made of heavy stuff. This would be like that salad dressing jar, all the heavy stuff that gets on the bottom. Okay? This is the iron nickel core. Now, they're both kind of made of the same stuff, the inner and the outer core. It's the core. But because the deeper you go in the earth, the more the pressure increases, the greater the pressure. Well, if you pressurize rock enough without even heating it, if you pressurize it enough, it will turn into a liquid. If you pressurize it even more, it turns back into a solid. Pretty sure. I'm not sure the physics of it, just know that that's what's going on. We have an inner core that's really, really, really hard, solid stuff. And it actually spins in the liquid outer core. So this is fascinating stuff, and this tells you right now that Brendan Fraser's movie Journey to the Center of the Earth could not happen. Okay.
Have you made?
Because you go to the core, it's liquid rock. We have evidence that I will show you in just a second. Okay? So, we even think that the inner core spinning causes our magnetic field. The inner core made of like an iron-rich metal that's spinning at a different rate than the Earth is, causes a differential field, which causes our magnetic field, which prevents our atmosphere from blowing up into space. Oh, I thought that was more exciting than you did. Okay. Okay, that's the core. All right. So I gotta answer Jonas's question. All right. Before Huck gets on the air. Okay. Guys, don't believe I dismissed class yet. Okay. If we measure these earthquakes, we can see that the body earthquakes go through the earth. Now, I want to give you guys, if you're at a swimming pool, and they're cleaning the pool, so some lifeguard's got some hole sticking into the water, what does it look like underwater?
It looks like
It bends, right? That's called what? Refraction. Guess what? The P waves and the S waves get refracted. Specifically the P waves. Alright. This is actually very important. I need you to pay attention, okay?
So that's what it said.
Between 100 and 140 is important. This is a shadow zone. This is really important, so I'd write this down while I'm talking. Okay, if we have an earthquake here, it sends out P waves, S waves. The S waves move about 60% slower than the P waves. So the further away you get, you can tell how far the earthquake is. Well, once something cool happens is that no matter where the earthquake, on the other side of the earth, 100 degrees to 140 degrees away from the earthquake, you get a shadow zone. What does the shadow zone define?
Please pardon this interruption.
No, I'm
Two announcements. The CFPA Council will meet
Alright, I'm not done.
Tuesday, February 4th at 2:15 in the Edis Room. That's room 1000. All council members should be present. The meeting is also open to interested CFPA students from all concentrations. Today, students who ride bus 8 will ride bus 698. Students who ride bus 99 will ride bus 768. Bus 152 is located in the B lane in the tunnel. That's it for the announcement. Thank you.
Okay, let me finish. Hold your question. Okay. Because we see the shadow zone, scientists are like, why don't we see S waves? Anywhere between 100 and 100 degrees. Why don't we see them? Well, what do S waves not travel through? They travel through solids. What do they not? They don't travel through liquids. So we see that there's this nice area here where there are 0 waves. And then they notice the P waves. The P waves come in here and start getting refracted. Well, we know what kind of stuff refracts what kind of stuff. We can measure that. We can do tests with that. And we found that, well, look, all these waves are hitting this, whatever this is, and being refracted and coming out down here. So we have this nice shadow zone where we don't see anything at all. And that told us, oh, ding, 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 there must be something liquid in the center of the Earth. Because if there wasn't something liquid, put it away, if there wasn't something liquid, then we would see the waves propagate uniformly around the Earth, but they don't. And then we can see how the P waves come in here and they get refracted, and then they get refracted again and again and again. And we study how these things are refracted all around the Earth, because we have tons of seismographs, Jonas. Okay? So, to answer your question, Jonas, how do we know what all this stuff is? It was my big question too. How do we know? We can study the seismic waves given off by multiple earthquakes, take data with seismographs, determining where the waves hit. I very likely will ask a test question that goes along the lines of this. How do we know that there's layers of the Earth? And you're going to have to answer something along the lines of, well, P waves and S waves go through the Earth. The S waves don't go through liquids, and because of the shadow zones we see...
One more announcement, girls soccer conditioning.
Because of the shadow zones that we see, that's why we have